Let's look at some important trigonometric limits. At the start of the unit on limits, we looked closely at y equals sine x over x near x equals 0 using graphical and numerical methods. And we came to the conclusion that the limit as x approaches 0 of sine x over x is equal to 1. Although we didn't show a rigorous proof, we can see from the graph here that as I approach 0 from both sides, I am getting closer to 1. So there are some pretty cool proofs out there involving geometry, and later we'll use L'Hopital's rule to show that this is true, but for now, we'll accept this as an important trig limit. We also have the following limits involving trigonometric functions. We're going to suppose n is a real number. Then the limit as x approaches 0 of sine of nx over nx is equal to 1. So similar to the previous example, except now there's a real number n in front of x inside the sine function and in the denominator. And it turns out that that limit is also 1. And if I take the reciprocal of that function, so the limit as x approaches 0 of nx over sine of nx, that's also equal to 1. Now we also have some other trig limits. The limit as x approaches 0 of 1 minus cosine x over x and cosine x minus 1 over x, those are equal to 0. And that comes up a little bit later in proving a trig derivative. And we can again show it later using L'Hopital's rule, but for now I'm just going to go ahead and show you the graphs just to convince you that as I approach x equals 0, we are getting closer to 0 on both of those two functions. Let's take a look at the limit as x approaches 0 of sine of 4x over 3x. If I try direct substitution, I am going to get 0 over 0, an indeterminate form. So here, I want to recognize that this looks really similar to that special form where the limit would just equal 1, except instead of sine of 4x over 4x, I have a 3x in the denominator. So what I'm going to do is pull out the 1/3, that constant multiple in there, and that's going to leave me with 1/3 the limit as x approaches 0 of sine of 4x over just x. Again, I really want a 4x in the denominator, so I'm going to put a 4 in the denominator, but that changes the problem. So I also have to multiply the numerator by 4. And now 4 divided by 4 is 1, so I haven't changed the problem at all. I've just rewritten it in a clever way. Now I want to take that 4 in the numerator and pull that out as well and multiply it to the 1/3 in the front, leaving me with 4/3, the limit as x approaches 0, of sine of 4x over 4x. So I do have that nice form where I know that this limit is equal to 1. So that's multiplied by the 4/3 in front for a final answer of 4/3. We will have other techniques to evaluate this limit, but this is a really important strategy to learn because it's seen throughout calculus, the idea of multiplying the numerator and denominator by the same thing to rewrite an expression in a clever way. For this limit as x approaches 0 of x squared plus 2x over sine of 3x, again, direct substitution would give me 0 over 0, indeterminate, so we're going to use another strategy. And this has that sine of 3x or sine of nx in the denominator, so what I really want is that same inside or argument of sine to be in the numerator. I want a 3x up here, but I actually have a sum up here. So let's start the problem by factoring the numerator. So my numerator, I can factor out an x, and then I'm left with the quantity x plus 2 over sine of 3x. All right, so what I really want in the numerator is just a 3x. So I'm going to actually just split up x times x plus 2 in a more spread out way. So I'm going to write this as x over sine of 3x times the quantity x plus 2 off to the right. So really, I've just kind of, again, spread out the multiplication just so that I can clearly see that I'm starting to form that special trig limit. And so I really want a 3 right here next to the x, so let's go ahead and put it there. But if I put a 3 in the numerator, I also have to put a 3 in the denominator. I'm going to choose to put it over here in the denominator of x plus 2. Okay, so now my limit laws tell me that I can go ahead and split this up into two limits. So I can think about this as the limit as x approaches 0 of 3x over sine of 3x, which we know is 1, times the limit as x approaches 0 of x plus 2 over 3. So again, the first limit is 1, and the second limit we can evaluate with substitution. If I substitute in 0, 0 plus 2 is 2, and so I get just 2/3. So I have 1 times 2/3 for a final answer of 2/3. Here we have the limit as x approaches 0 of tangent of 2x over x times cosine of 3x. Direct substitution does give us 0 over 0 indeterminate, so we're going to try some other strategies here. Now, I don't see a sine of nx anywhere, so I might not immediately be thinking about that trig limit we've been using, but let's remember that we can rewrite tangent of 2x as sine of 2x over cosine of 2x. So that's how I'm going to start this problem. I'm going to rewrite it as the limit as x approaches 0 of sine of 2x over, I already have an x and a cosine 3x in the denominator, and what's going to join it is a cosine 2x. So we've rewritten tangent using an identity, and now I can start to see that sine of 2x over x, but of course I'm going to need it to be a 2x. So I'm going to go ahead and move the cosine functions over. So I'm going to write this as the limit as x approaches 0 of sine of 2x over x times 1 over those cosine functions, cosine 3x, cosine 2x. All right, so I really want, again, sine of 2x over 2x, so I'm going to go ahead and multiply the x on the bottom by a 2, which means I also need to multiply the numerator by a 2, and I'll put it over here. And so now we'll split it up into two limits. Using limit laws, we are allowed to do that. And again, the first limit, by design, we got it to equal 1. And the second limit can be evaluated with direct substitution because cosine of 0 is 1. So I just have 2 over 1 here. So times 2, so we get a final answer of 2. Now, just as a quick reminder, we don't want to make one of the common mistakes, which is thinking that we can take a constant multiple out of a trig function. So these expressions, tangent of 2x, cosine of 3x, sine of 2x, we cannot simply factor out or pull out the constant multiple there. So we have special identities for certain situations, like sine of 2x has an identity, but that's not the route that we want to take here to use this special trig limit. So just be careful about not making up rules about trig functions.